Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's our great pleasure to have Jun Xu from Georgia Institute of Technology to come to Microsoft Research and give us a talk on his research work. What's happening?
I should get powered on. Go ahead.
Okay. Jun get his PhD from Ohio State University in year 2000. In year 2003, he received NSF Career Award on his contributions on basically established performance bound for networking. In year, I believe it's 2006 and 2008.
The IBM gave me some.
Yeah. He received IBM Faculty Award. Jun done a series of wonderful work related to computer networks. Performance evaluation, measurement, established bound, and so on. Without further ado, let's hear what Jun has to talk about on network data streaming and his journey in signal processing.
Okay, thanks for a nice introduction. So I think actually I've been giving this talk many times, but the last time when I came to Microsoft Research to give a talk, that was in a different building. This December 2004. I'm not sure how many of you are in the audience. None. Which is good. So I think we are using different.
You need the book again. That's fine.
No, we were using a different title actually. I think because I didn't think about this title until probably 2005 or 2006. So it's a different title, and actually at that time I only did like probably less than a quarter of my data streaming work by like December 2004. So I think when I did the talk last time, I think a lot of this work has not been done. So, but but I may spend the first 20 minutes talking about the work which I talked about in year 2004, which I guess is okay since many of you are not there. So for the work described in this slide file, I think this is done. There's a joint work with my former PhD student Abhishek Kumar, Minho Sun, Qi Zhao, and the collaborators from IBM like Zheng Liu and Jia Wang from AT&T. And I'm at Georgia Tech and as a faculty in the networking and the telecom group. So the reason why I call it computer science journey in signal processing is because my educational background is 100% CS. So I've never taken any course in electrical engineering, but it turns out when I study the problem in this area, I have to familiar myself with a lot of electrical engineering concepts like coding theory, information theory, these things. Although they may not be explicit in the work, but you have to have this type of understanding to basically pursue this line of research. Of course, after you do the research, you describe the result, you may not use any of the terms from the theory. But we do use techniques from that. So now let's talk about the motivation for network monitoring. So we have to monitor, why? So basically we want to motivate why we need network data streaming to monitor a computer network, why traditional techniques for monitoring will not work. So the reason is in the future we need to monitor computer networks for a lot of different quantities. Some quantities like elephant flows, we want to find the largest flows inside network. Largest flows means those flows which occupy the majority packets, has the majority packets. And sometimes we want to find the number of distinct flows. We want to count how many flows are there, and sometimes we want to find the average flow size. Actually, the number of flows and the average flow size are equivalent because when they multiply together, that's total number of packets in a time frame, which you can easily count. So if you know one quantity, you know the other. There are also other quantities you might be interested in, like a flow size distribution. So all these have applications in networking. For example, if you find elephant flows, you can do traffic engineering, which means you want to ship the elephant flows properly. You don't care about too much about mice because they don't occupy too much traffic anyway. And all these number of distinct flows, etc., they're useful for queue management, right? But remember, when you divide the bandwidth, you need to divide the bandwidth among all these flows. You need to know how many flows. I mean, you need to divide this kind of limited bandwidth by how many flows. So there's also, I mean, we talk about flow size distribution. It's useful for anomaly detection because, for example, a flow size distribution means you want to know how many flows have size 1. Size 1 means have one packet in it. How many flows have size 2? How many flows have size 3? I mean, one typical application I often talk about is in old days when you have a virus or worm, it has usually it has a fixed size, like 1,000 bytes or something. So if you divide the typical MTU, the minimum, it's called the minimum transmission unit in the internet is like 500, 512 bytes plus the header, all these things.
1500 I think. 1536 bytes.
The socket 576. I think that's a socket. That's really a socket length, which means it's different from one OS to another. Some OS choose to send out 512 byte chunks. Some OS choose to send out 536 byte chunks.
Probably a little bit larger.
Yeah. So you can think about 1,000 byte worm will be cut into 2 packets. So you can think about all these worm flows have size 2. So suddenly, if you have epidemic of a particular type of worm, which is two packets long, then you will see a lot of flows of size 2. So if your usual profile of flow size 2 is like 1,000 flows within a 5-minute time frame, you suddenly see 10,000 flows of size 2 within like a 5-minute time frame, then it may indicate some kind of worm propagation type of behavior. And there's lots of other quantities you want to measure, like per flow traffic volume. You want to, given any flow ID, you want to know how much traffic it contains, approximately. So I mean that's also useful for anomaly detection, and actually we also oftentimes need to measure this entropy of traffic. It turns out entropy is a very important quantity. I visited CMU, I think in 2004, and they talk about the need for measuring the entropy of the traffic at a certain node. The reason they want to do it is they have a network of something like 1,000 nodes, but they only have enough like a computation power to monitor all the traffic on 10 nodes at a time. So you can think about a town. There's a town which have 1,000 people, but you don't hire 1,000 policemen to protect 1,000 people, right? You cannot afford that usually. So usually a town of 1,000 people, you only have 10 policemen, right? So their idea is this kind of entropy. Hopefully, you can design like a data streaming type of algorithm to measure the entropy of traffic, and then when the entropy of traffic looks suspicious, which means, and then you ship all the traffic on this particular node for additional for like a further analysis. So just like you only when the citizen inside this town is threatened, they call 911, right? And then policemen come. So usually 10 policemen enough to handle all the 911 calls. So that's basically their picture. But they need an entropy estimation algorithm, and they formulate this problem. And I came back from CMU and I worked on it with my student, and we solved the problem in a month. And then we actually write a paper together with the CMU team. So these are all coming from the real applications. It's not like I'm sort of lock myself in my office and thinking about the paper I have to send next year and come up with this problem. So these are not artificial problems. They really come from the real applications. So by the way, some of you may wonder why entropy of traffic may indicate anomaly detection. For example, when you have a DDoS attack, then you have lots of singleton flows. And when you have lots of singleton flows, they increase the entropy, empirical amplitude of the network traffic. So actually, it turns out there are a lot of unlikely applications of data streaming, like a traffic matrix estimation can be viewed as a data streaming problem. Peer-to-peer routing can be viewed as a data streaming problem. And peer-to-peer routing, for example, in the unstructured peer-to-peer network, not DHT, but talking about the BitTorrent type of network. So I think it can be formulated as a data streaming problem. We actually have a paper on that. And even IP traceback can be viewed as like a data streaming problem. And we have papers on all these things. So the challenge of high-speed network monitoring is tremendous because simply because it's high speed, packets arrive it turns out packets arrive every 8 nanoseconds on a 40 gigabits per second link if you're talking about minimum length packet. I wrote 25 nanosecond here because I'm assuming 1,000 bits per packet, which I called it Craig-Partridge constant, because Craig-Partridge paper has like 1,000 bits per packet in it, so I feel it's safe to put 1,000 and nobody will criticize it. So, but in reality, if you assume minimum packet length, we're talking about 8 nanoseconds per packet. So, so you have to use SRAM for per packet processing. Unfortunately, per flow state is too large to be put into SRAM because you could have millions of flows, and if you put all the flow state into SRAM, I think it's just too large for SRAM. And so the traditional solution, because your SRAM is too small to do per flow processing, so traditional solution is to use sampling, which means you only sample a small percentage of packets, but because after sampling your traffic stream become much slower, so DRAM is fast enough for handle all the packets after sampling. And so you process all these packets using per flow state stored in slow memory like DRAM. And then, but of course, you didn't see all the traffic, right? Which means your per flow state does not record all the traffic. It only record, for example, one out of 100 of traffic or something like that. So you have to use some type of scaling to recover the original statistics. And if the sampling rate is very low, then you have to blow up like more times, so that it causes high inaccuracy. Because after scaling, you also scale the noise. And we are fighting losing costs because the link speed gets faster and faster. For example, right now at AT&T, their sampling rate is, I think, right now it's 1/500, which means you sample 1 out of 500 packets. But with link speed goes up, they're talking about the 1/5,000 packets. And so I think with this kind of sampling rate, your accuracy is not going to be very high with sampling. So network data streaming is offered as a smarter solution. So the computation model for network data streaming is basically process long stream of data like in one pass, which means you look at this packet, you decide whether you use it to change your internal state. If you decide not to change internal state and it goes away, later on you cannot change your mind, which means you cannot say, oh, I seem to see this packet like 1 second ago, but it's gone, so can I get it back? You cannot. So if you have one pass, you have to make a real-time decision. And of course, if you have infinite amount of memory, then it's no big deal because you just store everything. But it turns out you have very limited amount of memory, so you have to be very judicious on what do you store in this limited amount of high-speed memory. So the problem to solve is basically you need to answer. So I think if some of you are like a video coding people here, this problem is actually can be viewed as an online rate distortion problem. So you want to compress the data, you want to compress data, but you have to make a real-time solution. Not like image compression, you can scan it 1,000 times. So I think you have to make real-time, like a rate distortion decision. So the problem to solve, you need to answer some queries about the stream at the end or continuously. And you can think about this is like the goal. And you can actually translate it into the distortion function, the rate distortion function. So the trick is to remember the most important information about the stream pertinent to the queries. So which means you are very much goal-oriented. If you try to remember everything, you know it's not possible, right, from information theory. So you try to remember most important information pertinent to the query. Compared with sampling, basically streaming peruses every piece of data for most important information, but sampling basically digests only a small percentage of data, but absorb all the information within this data. So that's the difference between sampling and the streaming. So my analogy is always as follows. I think when I was undergraduate, I remember I think studying is not my only interest. It's actually a minor part of my interests. And so I don't spend too much time studying courses, but I still want to get good grades at the end. So reasonably good grades at the end. So what I do is exactly streaming. So which means I have a very thick book, which I don't read for the whole semester, but at the end I'm going to stream through the book I only have time for one pass. I don't even have time to go back and forth. And then my memory for one day is pretty small. So because I think, so I have to remember the data stream basically means I think I need to answer important query relevant to the exams, which means I need to basically I have some idea about the query which will be given in the exam. So I basically go through this book in one pass with basically trying to remember most important information that is relevant to the exam the next day. So so basically that's basically algorithm. So obviously sampling algorithm does not work, which means sampling algorithm means if I read page 1 of the book, page 11, page 21 of the book, I'm not going to pass the exam, right? Because I don't get to the right context. So, but by doing this kind of smart streaming, I think I managed to I think get through my undergraduate years without studying too much, without actually learning too much. So now I want to give you a hello world example of data streaming. So you think about giving a long stream of data, you want to count the number of distinct elements in it. It's a 1985 problem, so it's a very old problem. It turns out already more than a dozen solutions has been proposed for different kind of, there's a pros and cons for all these like data streaming algorithms. They may be good for different contexts, etc. I'm not going to go through the list of them, but I'm only talk about the classical one. So you think about the data stream is ABCA, CBDA, and obviously you know the number of distinct elements is 4, right? But if I'm throwing like 1 trillion elements on board and among them maybe millions of them are distinct, I think there are millions of distinct elements, you're not going to be able to count the number. So I think I want to talk about a simple algorithm here. The simple algorithm, you choose a hash function h with a range 0 and 1. I mean, basically, it hashed into a uniform random variable, and then let D1, D2 be like D1, D2, D3 be the data items. So you hash each and every data item, and you always remember the smallest hash value. Is that easy? You keep one register, right? You set to be plus infinity, and everything comes in. You compare, you hash, you compare with it, and you set to the smaller of the comparison, right? So you keep doing that. You can always remember the minimum of the hash value you have seen so far. And then we can easily prove that the expectation of this you can view it as a random variable because the randomness comes from the hashing. Okay, you can view it as a random variable. So you can prove that the expectation of this random variable is 1 over f0. F0 is the number of distinct elements among this data stream, plus 1. You can prove that because the minimum you can actually show it's a beta random variable, and you can do the expectation of this. And then obviously with one such hash function your accuracy is not going to be very good, but you can always have like 100 different hash functions, and then you can average up 100 of such estimates. Although I think to make things simple, I just say averaging, but for those of you who study statistics, you know that median or estimator often works better than the mean estimator. And actually, in some scenarios, people come up with more advanced estimators, such as harmonic mean estimator, like in stable distribution with small p, things like that. So averaging just one generic way to say it, but there's many ways of averaging it. So you can make accuracy much higher. So now we're ready to talk about our data streaming work. I think this is one of our earliest data streaming work, and it turns out to be instant success, which means I think this is actually the second piece of our data streaming work, and they received the best student paper award from the ACM Sigmatrix 2004. So the problem is to estimate the probability distribution of flow sizes. Basically, want to know how many flows have size 1, how many flows have size 2, and how many flows have size 3, and so on and so forth. So the application is, I mean, we already talked about application traffic categorization, engineering, network billing, accounting, anomaly detection. I mean, it all depends on this flow size distribution estimation. It's also very important because once you have distribution, you have everything else. If you want to ask the first moment, you have first moment, you have second, you want the second moment, you have second moment. Whatever you want, you can estimate from the distribution. So definition of flow is very flexible, which means typically we talk about flow as a bunch of packets with the same source IP, destination IP, source port, destination port. That's a typical definition of flow, but it could be different, which means it's a generic definition. For example, sometimes we just use source IP and the destination. I'm sorry, the source IP and destination IP as a flow, right? You don't care about the port numbers. This could also be a flow. So I think the definition is basically very flexible. So the architecture of a solution is very simple. I think it's basically what we call lossy data structure. We maintain an array of counters in fast memory. Counter just means it's an array, and each element inside the array is a counter. It counts from 0 every time you increment by 1. It's just that simple. And for each packet, a counter is chosen through hashing and incremented. I'm going to have the animation on that. And there's no attempt to detect or resolve collisions, which means if two flows hash to the same counter, we let it be, and we will have some way to recover. We will have some statistical means to recover from this kind of collision. And every 64-bit counter only, and we have some additional innovation later on, so that every 64-bit counter only uses 4 bits of SRAM. So which means, think about some flows can be very large, so the value can go beyond like 4 billion. So you may use more than 32 bits. So each counter you have to make it like a maximum size, and 64 typically is large enough. But if you make every counter 64 bits, it's too wasteful because this counter has to be in SRAM. So you want to reduce the size of counter, and there are certain systematic means to do it, which I'm going to talk about in the second half of the talk. So data collection is lossy, but it's very fast. I'm going to give you the animation. So you think about this is a processor, this is an array of counters. Packets comes in, you hash its flow ID, it goes to a particular location, and increment the counter by 1. So you can think about your counter value goes from 0 to 1. And then another packet comes, it belongs to a different flow, it goes to a different counter, it is also incremented, value goes from 0 to 1. And then the packet that belongs to the same flow comes, it should go to the same counter, obviously, the value goes to 2. And then a new flow, a third flow comes. Unfortunately, it's flow ID, so the hash to the same value as the red one. So but here I show you that there's 2 red and 1 yellow, but in reality, you don't have these, right? You don't have this tag. So you only have this value, so you don't know it, so you still change the value from 2 to 3. Make sense? So you have collision, but you don't know it. Okay. So that's basically the encoding algorithm, and what matters is the decoding. So I want to show you this is the raw counter values after basically after all the increments. This is the raw counter values. So we are talking about a trace from AT&T and a data trace, packet trace from AT&T, and it has about 1 million flows inside it. I think it's like 10-minute. I think it's probably 5-minute or 10-minute traffic trace, and it has like 1 million flows in it. I'm sorry, this is 1 hour. This 1 hour trace has like 1 million flows, about 1 million flows in it. But so this is the actual flow size distribution. This is the flow size. This is basically the frequency. So you can think about this is like a 300,000 flows of size 1, something like that, and it goes down like this. And then these are the other curves. The other curves are the raw counter value distribution. So for example, this is where you have 1 million counters. When you have 1 million counters, the raw counter values is this curve. And when you have 500,000 counters, this is a curve. When you have like 250,000, basically this one is a curve, so on and so forth. And you may say, okay, the difference is not that large, especially between these 2 curves, but it's not the case because this is on a log scale. So I think you're talking about the difference between something like 200,000. You decode as 200,000 flows, but it's actually something like 400,000 flows. So there's a huge difference down there because log scale. So the
those flows are not that big, right? We don't really care about them anyway. It seems they all converge kind of.
Well, this means when the flow size, for example, when you estimate flows of size like 80, then you don't get too much error. To a certain extent, you don't get too much error. But but when you estimate the flows, the number of flows of size 1, your error is huge.
Do you care about flows?
In some situations you have to care about it, because for example if you want to know whether you are under DDoS attack, especially for these ISP like AT&T, they care about it because you scrub. They provide scrubbing service. You scrub the DDoS traffic for the customers. So you first have to detect it for certain customers. And actually, yeah. So I think, for example, the usual number of flows of size 1 is 200,000, but during attack it could be 400,000. If you cannot distinguish between 200,000 and 400,000, then you may miss a DDoS attack or something.
So you don't know what kind of collisions you were getting for those?
This is just raw counter values. I just want to give you some idea. If you just treat raw counter values as a flow size distribution, this is the kind of error you're going to get. And of course, we're not going to treat it as it is, so we are going to have some treatment. So basically we are going to estimate the flow size distribution from these raw counter values. But that's all we got, so we have to do some estimation. So first we would do some quick and dirty ones. I think let's see. First, let the total number of counters be m. So this is a known quantity. Let the number of value 0 counters be m0. This is also a known quantity, right? We can see how many counters has value 0. Then immediately you can estimate the total number of flows, which can be estimated as n hat equal to m, which is this quantity times log. This is the natural log, m over m0. All these are known quantities, so this is a pretty good estimator. And then you can, starting from here, you can estimate the number of flows of size 1. How do you estimate it? You let the number of value 1 counters be y1. This is a known quantity, right? You can scan all these counters. You count how many ones are there. Then you can come up with a pretty good estimate of number of flows of size 1 as n1 hat equal to y1, which is this quantity, equal to e raised to power n hat, which is this estimator. This estimator, of course, is equal to this known quantity, and over m. So conceivably, you can generalize this process, which means you get n1 hat, then you can start to do n2 hat. You can do that. You can generalize this process to estimate n2, n3, and so on and so forth. But this approach is not going to work. Why? Because you can see n1 hat has n hat inside it. And indeed, if you estimate n2 hat, you're going to have n1 hat and n hat in it. So you're going to estimate n100 hat, it's going to have n99, n98 hat, all these things in it. So your error accumulates, which is not good. So you need a holistic solution, which is a joint estimation using the expectation maximization algorithm. So instead of doing this sequentially, you do a holistic, you do it in a holistic fashion. So you estimate the entire distribution using the expectation maximization. The solution is basically very commonsensical. You begin, it's an EM algorithm, so you begin with a guess of the flow size distribution, which is this one. Based on this guess, based on this guess basically gives you a probability space. Then you look at all the counter values, and you reason on how these counter values are going to split probabilistically. And how do you split probabilistically depends on the probability space induced by this guess. Okay. And then, so based on this, you compute various possible ways of splitting a particular counter value in the respective probability of such events. This allows us to compute a refined estimate of flow size distribution, which means when you actually split these counters according to the result of this Bayesian statistics, then you are going to get a new distribution. And this new distribution will be used to do this whole thing again. And then you repeat this multiple times, allows the estimate to converge to a local maximum. And this is basically the spirit of the expectation maximization. So I want to give you an example. For example, a counter of value 3 could be caused by 3 such events. 3 equal to 3 means there's no, if you see a counter of value 3, it's indeed a flow size 3. Or 3 equal to 1 plus 2 means a flow size 1 collided with flow size 2 into showing up as 3. I think 3 equal to 1 plus 1 plus 1 means 3 flow size 1 colliding into a flow size 3 into the same location. suppose the respective probability of these three events are 0.5, 0.3, and 0.2 respectively. And how to compute this probability? Basically, it's like remember you have initial probability, so you can compute the a priori, and then based on what you observe, you can compute the a posteriori using the Bayesian formula stuff. So it's pretty standard thing. So suppose the probability, the a posteriori probability is 0.5, 0.3, 0.2. Then suppose you have 1,000 counters with value 3. Then you just claim 500, 300, and 200 of these counters split in these three ways, right? That's expectation, which means you. And then what do we mean by split? It means if, for example, 500 of them split this way, these 500 splits will not result in a fragment of size 1, right? 3 equals 3, there's no fragment of size 1. But 300 of them split this way, each of them contribute to one fragment of size 1, right? And 200 of them split this way, but each such split has 3 fragments of size 1. So 200 times 3. So you credit 900 to your count of the flows of size 1. So you of course, this is just flows of size 3, but you do this to flow size all the flows of size 2, all the flows size 3, all the flows size 4, so on and so forth. And then you will get a bunch of new counts, and you treat these new counts as a new distribution. So you do this sort of over and over until it converges.
Let me see. I'm not so sure about the convergence part. So, basically, after this analysis, I credit 900 to N1, basically, this is 300 to N2, and 500 to N3.
No, let's see. 300 to N3, and let's see. I'll say 500 to N3, yes. 300 to N2, yes.
How I should iterate again?
Let me see if I have that slide. I'm not sure if I have it. Okay, I don't have that slide. Okay. Once you have all these N1 at the final count of N1, N2, N3, right? Then it turns out that they normalize into probability values, right? The percentage of it is this, and then it turns out that it really goes into how you compute a priori distribution. The a priori distribution is basically the hashing. If you look at a particular location, basically you're talking about the hashing process, right? And the hashing process is often modeled as the Poisson. It's modeled as Poisson. So you can think about these N1, N2 values as translated into the lambda inside these Poisson. And all these Poisson, of course, multiply together or whatever. And when all these Poisson multiply together, you do the normalization, it becomes something called Dirichlet distribution. So basically, initially you start with a guess of the flow size distribution, and then you get all these lambda, right? You get all these lambda, and then you get new lambda. By normalizing, you get new lambda, and then you keep doing this. And then, of course, you have a Bayesian step, which computes, which the result of this Bayesian step is this. So that's basically the spirit of the algorithm. So, but I don't have this slide here because I think. And it's EML algorithm, and people prove EML algorithm will guarantee to converge. Doesn't necessarily converge to the maximum likelihood estimate, unfortunately. So this one shows you the actual result. So this one, you remember, I already showed these curves before. So basically, this one is the actual flow size distribution. This is the raw counter values when you have 1 million counters, which means when you have almost equal number of counters as the number of flows. But still, you see the difference is quite a lot. And then we're supposed to show 3 curves, but I only show you 2 curves. And the reason is that our estimation sort of overlaps with the actual number of flows pretty well. And of course, if it's completely identical, it looks fishy. So to avoid that, I think we added some glitches here and there. So there's some sort of difference here and there. But I think it overlaps pretty well. And of course, some of you may say I hide the difference by drawing it as the sort of they call it the log scale, right? I draw the log scale, but the actual difference is bounded by around like 2% to 3%. It's not that much difference. I mean, overall, I think the difference is around the 2 to 3%. 2 to 3%
is manual difference between the actual and the estimate.
Yeah, so you can think about, for example, you have your actual number for flow size 1 is 400,000, so you make errors around maybe 80,000. I'm sorry, not 80,000. 80,000 like will be 20%, like 8,000.
I don't think you can actually bound the performance of this model.
It's not bound. It's just that's empirical. The empirical rate you are like 5% different. Yeah, because not even likelihood estimate you cannot bound its performance. So and so our sort of estimation works really well. And I think we have a bunch of other experiments. I think this is this one comparison with sampling. You can see this means you sample with probability 0.1. I mean 1 over 10, and then you estimate from sampling. I think AT&T Nick Duffield has and his group have some algorithm of inverting the sampling, which also use EM algorithm. And this is sort of you invert from 10% sampling. This is when you invert from 1% sampling. You can see that the actual flow size distribution is basically covered very well by our algorithm. Okay, it's covered very well by our algorithm, but you can see inverting from sampling performs very badly because it's really a moving average. It's really a moving average. It cannot witness the ups and downs in this kind of flow size distribution, which can be important in anomaly detection type of purposes. And the reason why it's moving average is, for example, if you recover from sampling, say 1 out of 100, if you see a flow size 1, you don't really know if it's actual flow size 1 or it's actual flow size 10, it's actual flow size 100. You have no idea, I think, where it comes from. So that's the reason I think sampling will not work very well. So I'm going to skip the next. Oh yeah, okay, that's the only one I put here. That's good. So that's sort of the flow size distribution work, and I think one technical problem which comes from this flow size distribution work is we have to use an array of counters, and each counter is like 64 bits, which is very expensive. Of course, I think people have designed certain algorithms earlier. It turns out that algorithm by George Varghese group, I think, require 9 plus 2 bits, which means 9 bits counter, 2 bits control, which is 11 bits. But 11 is a number which computer science people don't like, right? I mean, you don't have 11-bit SRAM or things like that. So we like nice number like 4, things like that. Okay. So I feel that we can do better, and so the problem statement is we want to maintain a large array of counters that need to be incremented by 1 in arbitrary fashion. So you think about you are maintaining this array A, and the customer comes up with this I1, I2, and when customer comes up with index increment by 1. So this sounds like a trivial problem, but it becomes non-trivial when the customer specifies such an increment every 8 nanoseconds. Then it becomes non-trivial, and also it becomes non-trivial when you want to spend as little money as possible. So increments don't come very fast, and the values of some counters may be large, right? Because some flows are large, so the counter can be large. But if you want to provision every counter to the worst case, you give everybody 64 bits, which can be very expensive. So you fit everything to an array of long SRAM counters can be very expensive, and also some of you may say caching may work, but actually caching will not work because you may not have locality in the access sequence. So motivation, it has lots of motivation. Of course, I mean, now I put it in this context, you will think it comes entirely from data streaming, but it has lots of applications other than data streaming. So of course, I mean, the first motivation comes from data streaming called hash increment, right? You hash something and increment the counter. But there's also other motivation. For example, routers may need to keep track of many different counts. I mean, for example, count the packets among different source IP destination, source IP prefix destination IP prefix pairs. And it turns out I feel that this these kind of counter array can help us implement millions of token leaky buckets on routers. So Cisco people may be interested in this as well. And it's extensible to other, it's great, it's extensible to other non-CS applications and sewage management. So I'm going to talk about how, so you can think about if your subdivision has like 100,000 people, right? You think about 100,000 toilets, but you don't want to design a cesspool of 100,000 toilets, right? You want to design the cesspool to be smaller than the total size of all these toilets, right? So then I think this type of algorithm will work. And then our work basically is able to make 16 SRAM bits out of 1. They call the alchemy of 21st century. So the main idea in the previous, I think we didn't invent the main framework. I think this is invented in earlier work. I think its idea is basically all the counter increments goes to a very short SRAM counter. And then when the short SRAM counter becomes like overflowing, for example, if you have 8-bit SRAM counter, overflowing means that you're approaching 255, 256, then you will have a counter management algorithm to sort of flush these overflowing counters to the DRAM. The flushing means basically you also have, like, if you have 1 million SRAM counters, you also need 1 million DRAM counters. Each corresponds to each. So anything overflows, you just flush over there. For example, if this one overflows from 255 to 256, then you reset to be 0, you increment to 256 here. It's just that simple. It turns out this algorithm is very hard to design. Why? Because you can think about it, you have to work with arbitrary increment patterns. So for example, you could come up with policies, say, if you're half full, then you flush. But the adversary can make everybody like 127. Then you hit 128 simultaneously, then you're dead. So no matter how you come up with policy, you have to imagine there's an adversary case there which make your sort of strategy may not work. So this thing is extremely hard to design, it turns out.
How did it affect the speed of the overall operation? How often did you have to go to the overflow?
How often? Well, it depends on how large is your counter. So if a counter is short, then you overflow more often. If counter is longer, you overflow less often. Of course, you want to design something which is short as possible. So I think that's basically our competition, right? I think if we design something much shorter than the previous scheme, then I think we win. So, but of course, if we design to be much shorter, we have to come up with much smarter this to do it. So I think that's basically the challenge. So the previous approach has used different kind of counter management algorithm. I think actually CMA also stands for, I think in real life stands for they call the condo association or condo management association or something. So I think you can think about subdivision. My subdivision, I think, analogy, I think goes with that CMA. But anyway, so they have this, Nick McCune's team have this work, and they basically do the, I think, I call the fullest toilet first, right? And basically, if your counter value is the largest, then you have the highest priority to flush. So their algorithm is basically the fullest toilet first, and then I think the algorithm is not very efficient. For example, even when the SRAM DRAM speed difference 12. So you think about if the SRAM DRAM speed difference 12, then only 4 bits is enough, right? 4 bits is basically reduce the urgency by 16 times, right? 16 bigger than 12, so it's enough. But first they will need 8 bits, which is I think which is like twice as 4 bits. Another thing is because when you do because they implement the whole thing as a heap. With a heap, you have to have like a pointer, and when you have 1 million counters, log 1 million is like 20. So your pointer, I think your left pointer, right pointer to do the heap takes you I think you only need one. I don't know why. I think you probably only need 1 pointer. This pointer takes you 20 bits per counter just for the pointer, which is very wasteful. So the total is like 28 bits per counter, even though the theoretical minimum is 4. But they declare victory because they go down from 64 to 28. So, and they need the pipeline hardware implementation of a heap, which is non-trivial. And actually, energy-wise, it's not good because any time you have a pipeline, it costs some energy, right? I think. And the CMA used in there's a later work by George Verghese. It's much more efficient. I think they go down. I'm not going to go through the detail. They go down to 8 SRAM bits per counter, and the 2 bits for the control logic. So the Nick McKeown's team is like 8 plus 20, and they can do 8 plus 2. And the hardware logic is actually simpler than, probably I think simpler than the Nick McKeown's team solution. And our scheme does much better. I think our scheme only needs 4 bits, which is a minimum. And our idea is very simple. We flush only when the SRAM count is completely full. So it's like only completely full toilet can flush. That's basically the policy. And then we use a small SRAM FIFO buffer to hold the indices counter be flushed with DRAM. You can think about a very small cesspool to hold all the flushing like the toilets. And then there's a key innovation. There's a simple randomizing algorithm to ensure that the counters do not overflow in a burst large enough to overflow the FIFO buffer, which means if every household flush the toilet simultaneously, then I think then we are dead. So basically how do we do it? It's very simple. We set the initial values of the SRAM counters to independent random variable. It's like bootstrapping. You bootstrap at the very beginning. You set the initial counter values to uniform random variables. I mean, uniform randomly distributed between 0 and 15. Why 15? Because we're talking 4 bits. So there's only 0 to 15. Values only 0 to 15. So you set to be a uniform number. But of course, you're doing counting. So if you count, you have to count from 0, right? So you have to remember your seed value. And how do you remember? It's very simple. You just set the corresponding DRAM counter to the negative of your SRAM seed value, right? So you start from 0. And adversaries, now this is really an online algorithm contest. Adversaries knows our randomization scheme, but not the initial value SRAM counters. That's my coin toss. How does the adversary know? So, and then we prove rigorously that the small FIFO Q can ensure that the Q overflows with very small probability. So basically, this scheme basically this community has like ordinance, like a city ordinance. It says that when new homeowners move in, you have to set the water level in the toilet to a uniform random value, and then you say there's a small cesspool will work, I think, for a very long time. So let's look at the numerical example. For example, 1 million, you have 1 million counters. It's 4-bit SRAM, 64 DRAM, and the speed difference like 12. It's just like all these parameters like usual. And then for 1 million counters, you don't need 1 million. Like 1 million buffer slots. You only need, for example, 300 buffer slots in the FIFO queue for storing indices to be flushed. And then after like 10 raised to power 12, like a trillion counter increments in arbitrary fashion. So you can think about like 8 hours of 40 gigabits per second traffic. 40 million packets per second like links. After that many, so which means you can think about after 8 hours of like this kind of high speed, then the probability of overflowing from this FIFO queue is like 10 raised to power minus 14, which I think is exactly the digital fountain undecodability probability. So the mean time between failure for one of these router or counter is like 100 billion years, which is longer than the Big Bang. I think Big Bang is like 17 billion or something. So I actually went to Cisco to give this talk, and they told me that they are usually nervous about the randomized algorithm with this probability, but I think Flavio, so that's Flavio Bonomi, and he said he looks at 10 raised to the power minus 14, he feels pretty comfortable. He said if it's 10 raised to the minus 3, I think once every 1,000 years, I would think once every year is pretty it's pretty reasonable, but I think this is once 100 billion years, so it's even better. So. But even once a day, I think you're fine with it, right? You lose the counter value, so what? So, and I think I told them that this is California I think the probability of the mean time between earthquakes is like I don't know 100 years. Right? So anything better than 100 years will work in California. So and this place as well, right? I think this place also mean time between earthquakes probably 100 years or something. So the conclusion for that one, so data streaming is a very powerful tool for. I'm sorry, I don't know why I have this typo after so many years. So for network measurement and monitoring, so it's a challenging research problems arise due to stringent space and speed requirements. So I think, so actually we will need some, let's see, actually we didn't talk about distributed data streaming. We probably won't be able to have time to talk about it, but we actually do distributed data streaming as well. Distributed data streaming means you have lots of data streams and you want to find out some statistics about the union without actually unioning them, because unionism is just like shipping all the machines from a data center to a single machine and the processing, and you just cannot do that. So you think about you want to compute some statistics of all the data across all these like data center nodes, and you want to get some statistics, but without shipping all the data together, without reading every piece of data. So I think that's actually a pretty challenging thing. And I do have a second slide file, which is mathematically very exciting.
Before you continue,
okay.
The talk is not data streaming. Let me ask some questions.
That talk is data streaming.
That talk, okay?
Is data streaming, but go ahead.
I actually want to, basically, you know about this counter-break talk.
Sure, yeah.
Year.
Yes.
What's your comment on that, basically?
Well, counter-Braid's talk, I think, let me first summarize the counter-Braid's idea. So counter-Braid's idea basically is they want to be able to decode the size of each and every flow. So which means basically they need a sketch. Basically, you'll have a sketch, and then this sketch, and then they also gather all the flow IDs offline.
So basically, I think in addition to basically your hash, in the first part of the talk, they hashed multiple positions, and they try to use LDPC code.
Exactly, yeah. And also because they do the variable length encoding, which means they have fewer counters. They have like a pyramid type of scheme, which means they have fewer and fewer like higher order counter bits. I think so that you can save space. And then when a packet comes in, you hash its flow ID to multiple locations and increment it.
I think they argue they can do exact counting. So basically, here you are basically getting a probabilistic estimation.
They can. Well, they have more input than I do, and they have more output than I do. And basically, they can. They need the basically all the IDs. They need all the flow IDs to be stored, to be able to decode, because the flow ID is translated into the decoding matrix. Okay. Without decoding matrix, of course you can map the flow ID to decoding matrix and decode, but having the decoding matrix is basically the same as having all these IDs. So they need all the IDs, and with all the IDs, they can find out the flow size of each and every ID. So that's basically what they do.
Okay.
And
last argument, I'm not exactly sure, but we can ask them later on, because that's actually pretty tough, basically, storage requirement if you have to do that.
Okay, but their decoding is not like instant, which means you can, if you want to decode for each and every flow real time, you cannot. Basically, you have to spend like 30 seconds at the end to decode everyone. So if you decode in a batch for everyone, it costs you 30 seconds. If you amortize over all the counters, it may work.
Question I will ask
yeah, it's I think they actually cited I think several of our works. I think in it, including counter or things, because for example, our work did blow a hole in. I think to a certain extent, we did blow a hole into their work in the sense that, for example, we can do 64-bit to 4-bit, right? With this counter thing, I mean, there's no way they can go from 64-bit to 4-bit. So I think they have to argue that in certain applications you don't want DRAM to SRAM to DRAM traffic because that costs you bus traffic and things like that. And in these situations, I think their solution is entirely SRAM.
I think they also have some kind of mappings. I mean, they also have basically, I mean...
But they don't have SRAM to DRAM. They don't have SRAM to DRAM like traffic. So I think, yeah, but I think
I think they actually should be able to do that as well. I mean, because they potentially have a second stage. So basically, I mean, the second part of your flashing algorithm can work in there.
Oh, I think, yes, they can use mine, but they specifically say they don't want to use mine because I think they're underlining, because if they can use mine, nobody wants their work because if their work is like a complicated encoding and decoding. So they will be able to get exact count. They will get exact count, yeah. So, but basically what they could do is they get all the flow IDs, and they also use, for example, our algorithm. They could just use our counter array and to do it. So to motivate their work, they have to say that in certain situations you don't want SRAM to DRAM traffic, so they have to stay adding SRAM, so they have an SRAM only solution. So their solution is SRAM only.
I think one of the basic things I'm not that clear is if they actually need to know all the ID of the flow, or they just need to basically know
at least
the number of all the flows.
Right now they need all the IDs of flows, and they're working on some kind of partial decoding. There's some kind of partial decoding work going on. Because I had a very long conversation with authors, with both Balaji and the first author, the student.
Yeah.
So.
Another, basically, my question is this. This is actually the snapshot, basically. I mean, for you, I mean, during the counting time, transferring to SRAM to basically DRAM, I mean, you did a very nice work to basically create the basically flow on the thing. But basically, sometimes you need to get data out.
I see.
Right? I mean, for example, the counter-break guys, you also need to get the data out. I mean, then you basically need to take a snapshot of this picture. And the only thing I can think of is basically during the snapshot time, you have to stop counting.
Well, you could have what they call ping-pong buffer, which means you sort of throw in twice as much resources you need, or
it's basically shadow memory.
Shadow. You could do something kind of shadowing or something. So I tend not to deal with things like this because that's a separate issue. You could have some generic solution for things like that.
So of course, you would double the memory.
It may not be double. You can think about there could be some coding. There could even be some coding solution, but that's a different dimension, right? Because the shadow period is very small compared to the measurement period, because you're doing a sequential read, right? Because when you read out, it's a sequential read, so it's much faster than the random access read. So you can think about only 1/10 of it. So you can even imagine some error crashing code type of solution into it. But that's. But I want to isolate this as a generic. It's a generic problem, not just for this problem, but for many other such ping-pong buffer type of questions. So now I think I'm going to look at, let's see, it's a different slide file, and that's here. It's my student's Dimax talk. So it's a data streaming algorithm for estimating entropy of OD flows, and I choose to talk about this because first, this is distributed data streaming. That's the first thing. Second, it used some fancy math, and it turns out these fancy maths are very easy to understand. So I think, I think the connection, and this work connects very well with classical theory result. So sometimes, I think. If I don't have this kind of connection, I will feel very bad because it's like theory people are doing deep theory work, and there's some kind of suspicion that I'm sort of duplicating theory results by doing some randomization. I think by doing some obfuscation of the terms or things like that. But this one connects very well with the theory results. I think but I do check carefully that our work is not really sort of permutation or obfuscation of existing theory results. And the real, I have to be honest with you that the real value of this work, to be very honest, that I think it's still debatable. But I think mathematical wise, I think it's a beautiful work. So I think the problem is very simple. I think we did have a piece of work done in 2005 on estimating the entropy. We already talked about that. I'm not going to talk about that today because the technique there is pretty standard in theory. And but this problem is a much harder problem, which I think our entropy estimation solution is one of the earliest. I remember there has been about, let's see, I think around the same time there are about a dozen solutions on like entropy estimation. But none of these solutions are able to estimate the union or intersection, the entropy of the union and the intersection of two data streams. So you can estimate the entropy of a single data stream, but you're not able to estimate for a single data stream like S1, but you're not able to estimate the entropy of the intersection of data stream S1 and S2. But it turns out estimating the entropy of the intersection of the data streams is very important. And for example, you have OD flow, which means all the traffic that goes from the origin to a destination. You want to estimate the entropy of OD flow. What is OD flow? OD flow is basically all the traffic, the intersection of all the traffic goes from a particular origin to with all the traffic that goes to a particular destination, right? It's an intersection of these two data streams. So you can see that these three are intersection.
So these are
the ingress. You can think about these are like ingress points. These are like egress points of ISP.
Okay, you are looking at all the flows from basically
this is particular I, this is particular J.
Okay.
A particular O, this is particular D. We're talking about the entropy of all this OD flow traffic,
okay,
which is intersection of all the ingress traffic here and all the egress traffic here, right? Because you can see some traffic which originates from here but goes to somewhere else.
okay.
Some traffic goes to here but does not originate from here. So it's really intersection.
What information do we have in this problem?
What information do we have? The only information we have is everybody sees all the traffic that comes in, and everybody here sees all the traffic that comes out. That's the only information we have. We don't need any sort of communication. We do not need the communication, and basically the solution is you will digest the data stream. You get some sketch. You will digest data stream here. You'll get some sketch, and then you compare these two sketch. We will have some communication, but which is basically piecing together two sketch,
Okay.
which is much. But this is much smaller than the actual traffic. So now let's talk about entropy. So entropy is basically this quantity and this Cartesian. So this slide is made by my student, and I think I won't have this much time getting photo stuff, but I think he's done a much better slide than I usually do. So, and so this is the entropy definition, and you can think of Pi as a fraction of traffic from the ith flow. And what we measure is actually what we call the empirical entropy. It's not the actual entropy because the actual entropy is different from empirical entropy. Actual entropy requires to specify a model or things like that. We're not going to deal with it. We are measuring the empirical entropy of a data stream. It turns out that in many situations, estimating entropy is equivalent to estimating entropy norm. So this is something which is called the entropy norm, which is basically, you can think about the Pi is equal to Mi over M. So M is the total number of packets. So instead of estimating sigma Mi over M log Mi over M, you can estimate Mi log Mi. If you know M, these things are convertible. So Mi is the frequency of the ith flow. So it's often equivalent to estimate entropy norm, and it turns out entropy norm is much more manipulatable than entropy. So the motivation, there's a lot of motivation for entropy. I think there's anomaly detection, traffic clustering. I think everybody is very interested in entropy, and DDoS attacks, traffic engineering. So the theory we use is the theory of stable distributions, and the distribution D is called the p-stable if for any constant A1 to AN and the random variable X x1 to xn drawn from this p-stable distribution, a1 x1 plus plus an xn is the same as in distribution as this LP norm of this a1 to an times x. For example, Gaussian is stable because if you have x1 to xn as a standard Gaussian, then it's basically equal to this times the standard Gaussian distribution, right? The Gaussian distribution is basically p equal to 2. Okay. So I think this, right, because the variance add up, right? With Gaussian, the variance add up, and of course you have to divide by 1/2. So, and that's discovered in 1907 by Paul Levy. So I think so. Sometimes you regret you were not born 100 years ago, so or 200 years ago. Then the result could be discovered by you. So the property of stable distribution, we talk about it. So Gaussian is 2 stable, Cauchy is 1 stable, and closed forms are only known for these 3 values, and there are no formulas for generating samples from p-stable distributions. It's called Chambers formula. And now I think there has been existing piece of work. That's not my work. It's an Indic. Actually, this is his JSM paper. I think his conference paper was in 1999. It's much earlier. And then basically, he is able to figure out how to estimate the peak frequency moment of a data stream, which is in this form. So you can think about the mi is the number of packets in the flow I, and he can allow you to estimate sigma I mi raised to power p. Using the stable distribution. So basically, this is algorithm. For each flow, you draw a stably distributed xi, and the counter starts from 0, and then for every packet you see, you increment its sort of. You can think about there's a hash function which maps the flow ID to a stable distribution random variable. So you can see after you increment all the packets, then the final value is distributed as the LP norm of this flow side distribution times stable distribution, a standard stable distribution. I mean, you can easily to verify that. This is already done, I think, several years ago. And then this becomes a parameter estimation problem, right? And how do you do parameter estimation? You can do this experiments. You can do this experiments multiple times, and then you extract this quantity. And it turns out, so by the way, oftentimes we think about the mean estimator, but mean estimate does not work here because stable distribution is unstable in terms of I think this convergence of these things. And so this thing can be done using the median estimator. Median estimator works very well, but it turns out recently we discovered, I think some researchers, some statisticians discovered that when p approaches 0, then the median estimate does not work that well. So it turns out the harmonic mean estimator works very well, and things like that. So I think there has been a lot of research on what's the best estimator in these kind of contests. But anyway,
you only need the basic number of basic counters v, which is basically the independent number of times.
Exactly. Yeah. So and you need the independent hash functions, maybe 20 independent hash function, whatever. And this is actually I call the Christmas conjecture. So I think I thought about the conjecture. I think really around the Christmas Eve. So, and I was thinking because I want to estimate the entropy. Yep. So I was thinking, is it possible to represent this entropy function or entropy norm function by a linear combination of what we call power law functions? Mm-hmm. For example, something like this. It turns out we can. So I think my student actually figured out in one day that I told him, because I sort of write a small program, play with a MATLAB, but I always have a hump, which means I do the regression very well on most of the points, but there's always a hump somewhere here and there, and which I hate a lot. So I asked my student, how about ask my student to find out whether you can do at that time I asked him to do 4 approximation, which means approximate by 4 terms. But he actually returned the result which is much better. You can approximate by 2 terms.
Okay.
It turns out function like x log x can be approximated very well by a family of functions of this form, which means x raised to the power 1 plus alpha minus x raised to the power 1 minus alpha multiplied c. It turns out actually this c is actually equal to 1 over 2 times alpha. So something like that. So there's a family approximation, and it turns out the proof is straightforward using Taylor expansion. It's just Taylor expansion. And just look at the numerical value. I'm sorry, I apologize. This is not over 2. This is basically 10 times x raised to the power 1.05 minus this. So this is a typo. So let's see how well do we approximate x log x with this function in this interval. You can see the approximation is pretty well, right? It's pretty well, and one is the approximation, the other the actual curve. And you can see it's not much difference. And in fact, it goes pretty well until 5,000. I think 1,000. I think so. So you can approximate it pretty well within like 0 to 5,000. And then if you can approximate, then it's good because m1 log m1, because this is the entropy norm function. If m log 1 can be approximated as this, n log mn can approximate this, then you add up everything here, you get entropy norm. But you end up having here, you get something like L1 plus alpha norm, right? Except it's raised to power 1 plus alpha, and then you get something like L1 minus alpha norm. But we already know how to estimate the L1 plus alpha norm, L1 minus alpha norm. So we can just sort of take the difference. And oh, by the way, because as the approximation stops at like 5,000 or something, right? It gets worse beyond 5,000. But anything beyond 5,000 is elephant, right? It's a large flow, so we can have elephant detection module which handles all the flows larger than this kind of threshold. So which means tail we handle it, all the head basically we do approximation.
I assume you will use sampling to do elephant detection.
You could, yeah, I think you could use sampling. You could use something like a sticky sampling. There's some kind of data streaming algorithm which you can isolate almost all the elephants.
Okay.
And which I think works pretty well. I think these two pieces, and then I think this method. I think the LP norm method actually extends very well to the intersection case. And this is the extension. You can think about at the origin side. Based on this sketch, you can estimate the LP norm of all the ingress traffic, right? But suppose this is the OD flow, which means these are the common between O and D. But these are the cross traffic here, this is cross traffic there. So you can think about if you estimate the LP norm at the O side, then you get this, right? You estimate the traffic at the D side, you get this. Then you can actually, these sketches are linear, which means you can sketch, you can think about like a vector, a value vector, right? You can do the point-wise subtraction, you can do the point-wise addition, and then it turns out if you do the point-wise subtraction and you estimate the LP norm from it, you actually subtract these two things away. You basically get both cross-traffic part add up. And then you can also do a point-wise addition, and you estimate the LP norm. You get their sum. So you can see that we can come up with two different estimators. One is just O and the D minus all the cross traffic. You get one estimate of the OD flow, the LP norm of the OD flow traffic, right? Or you can subtract these two things, and both will give you an estimation of this one, which is the LP norm of the OD flow traffic. All these are this is cross traffic. All these are cross traffic. So which means the LP norm type of method extends very well to the intersection case. Okay, and then ours is just the difference between these LP norms. So we let the LP norm handle the intersection, then we take the difference, so we know the entropy norm of the intersection, which I think works pretty well. And we have a bunch of, and then it turns out that if to go from the entropy norm to entropy, we need to know the total number of packets during a certain time frame. It's trivial when it's a single data stream, right? Because you can count. You can count it, right? You only need a counter to count it, so it's trivial. But in the OD flow context, it's not trivial because it's OD flow traffic. It's called traffic matrix estimation, which is not trivial. So obviously, so traffic matrix estimation is actually itself is non-trivial problem. There's been a lot of papers on that, including I actually had a paper on traffic matrix estimation, and but it turns out that the OD flow traffic, which means the traffic matrix element, is exactly what we call L1 norm. So it is L1 norm. So we can actually use Cauchy distribution, which is a type of stable distribution, to estimate L1 norm using pure-to-index method. Yes, we can do it. But what we are doing something extra, right? Which means that beyond the L1 plus alpha norm and L1 minus alpha norm, we have to do L1 norm, which is the extra overhead. But it turns out because the alpha we use is typically very small, like L1 plus 0.5 norm and L0.95 norm. So it turns out that you can see the function, when alpha is small, this function approximates x very well. So therefore, the sum, you can think about the sum of L1.05 norm plus L0.95 norm divided by 2 approximates L1 norm pretty well. So based on that, so basically we are shooting two birds in one stone, right? Because once we have these two norms, when you add them up and divide by 2, you get the L1 norm, and when you take the difference, you get the entropy norm. So then we have both components we need to estimate the entropy of the OD flow traffic. So, and then so we have a lot of experiments with AT&T, and I think and we have a huge trace, and I think these are the experiments. So this is basically the relative error, I think, versus the fraction of experiments. So you can see the relative error is all three curves with relative error, I think, less than 15%. Also, what are these curves? These three curves means when we estimate the elephant, we have to use some sampling. So these are sampling probability for elephants. It turns out it's not very sensitive. So which means I think it's not very sensitive on this sampling probability, which means that how good your elephant detection solution does not impact this result very much. What's the intuition? The intuition is, if you're a large elephant, then you're going to impact our result significantly, right? But the larger elephant has a higher probability to be detected, right? But if you're smaller elephants, you can think about the elephant threshold of 5,000. So smaller elephant means 5,500, 6,000. If you're a small elephant, yes, the probability of that you are not detected is pretty high. But the error you cause is also small. So you can see this kind of aerodynamics of elephant detection works very well with our sort of entropy estimation. So that's basically the moral of the story. So I think we have other experiments, but I would rather just skip these results. And so basically, I think we are able to sort of extend the study of entropy of OD flows as a new tool for network tomography, and so we present the algorithm to solve the problem in practice with low relative error and reasonable resource usage. And we introduce a new type of distributed streaming problem, so basically the estimating statistics of origin destination flows. And I think I like this work. These are the conclusions by my students. So I think I probably will write it differently. But the thing which I like it best is we are able to connect to the mainstream data streaming work, which is the kind of theoretical LP norm. Because, for example, Indic have this paper for like more than 8-9 years. But of course, he has a bunch of applications, but these are all theory applications, which means you use theory result to do another theory result. And so it's like, to a certain extent, it's like self-licking ice cream. So, and but we are able to find something which comes from the real application need, and I think we can tap into. Basically, we find a very concrete practical application of his theoretical result. which is very exciting. And I think the connection is very simple after the fact. If I tell you this connection is very simple, but it's probably not that easy to think about like beforehand. So that's the reason that's the reason I think I like this work sort of very much personally. So
It's a very nice piece of work.
thanks.
I saw in the network routing context. I mean,
Mhm.
I'm trying to see what kind of application can be used in application context.
There has been some. We have a exponential decay Bloom filter, which has been quite useful for like peer-to-peer search, like a peer-to-peer search content sort of peer-to-peer content search type of application. And actually, people have been applying our result to like ad hoc network routing, because ad hoc you can think about identity of a node in ad hoc network is like it's like you can think about it like a object which needs to be searched.
We can probably talk offline.
Yeah, something like
Just
that.
wondering if there's any other questions from the audience.
So how many statistics do we have here? I think you can be liberal, I think, on the definition. So I think just want to get some sense.
Okay, maybe you can thank the speaker
Oh, thanks.
for the excellent talk.